that you can hear me well. Thank you for your time and for being here. And hope by the end of this quick lecture, I will leave you with something new that you learn. Today I'm going to talk about a project that we've done with Ceva. My company, the company I work for is called Optima. And we're talking about how we can converge on the ISO-26262 metrics. In this scenario, we were talking about the Ceva SensPro AI and Vision DSP. This is an IP provided, a shelf IP provided by Ceva, which can be used for automotive purposes and also for other applications. In this project that we worked on the automotive version of it. And the requirement for this IP was to meet the standard of ISO-26262 with the ASIL-B requirements as a safety element out of context. Now, what do we mean by safety elements out of context? When the designers design this IP, they are not totally know of the full details of how this IP will be used. So they need to keep this in their mind when they design the safety. The safety team in Ceva will have actually a functional safety plan. And this plan includes multiple hardware safety mechanisms, including parity, ECCs, and watchdogs. The main idea is to be able to detect random faults, but the main safety mechanism that is generally used in ASIL-B applications is what we call an STL, which is a software test library. So what is an STL? It's a common safety mechanism used mainly for ASIL-B CPUs, DSPs, and lately also in neural network chips. Since it is a software base, it is a very low, almost to none silicon cost safety mechanism, compared of course to dual lock steps. The main operation is actually you can run a software several times during the work of this chip, and the idea is to check whether an error happened in this chip or not. The software should detect random faults like stack at 1 and stack at 0 on a given gate or a given node. Now, when we are talking about the standard ISO-26262, they are defining several what we call ASIL level, automotive safety integrity level, and depending on the usage of this chip, a given level is dedicated for this IP, and each level needs to meet a specific requirements. There are two main metrics that we look in this scenario. Of course, there are a lot, but we will focus today in two of them. One of them is the DC, which is the diagnostic coverage, and the other one is the SPFM, single point fault metric. We'll explain them in a minute. So I'll just do a quick briefing of the terminology so we can speak in the same language. We'll start what is defined in the standard by calling it lambda S. Lambda S is actually the percentage of faults that actually have nothing to do with the critical functionality of the chip. Okay? We call this lambda S. The second lambda that we will define is lambda SPF, that stands for single point faults. This is the percentage of faults that actually have no detection mechanism covering them. So they can influence the critical outputs or the critical functionality of the chip, but have no detection mechanism covering them. And this is a scenario where we want to avoid. Okay, these we consider them the bad guys. Then we'll define the lambda RF. These are what is called residual faults. This is the percentage of the faults that can actually have a safety mechanism that can cover them, but the safety mechanism is not able to detect them. Okay? So by covering them, we mean that there is a kind of path between this fault and the safety mechanism, but in the current running test or running STL, the safety mechanism cannot detect them. Then we will define lambda MPF, which is one of the major parameters in this scenario. This is the percentage of the total faults that the safety mechanism can actually detect. And the parameter and the metric that we really care about is the SPFM, it's the last line, which is actually the sum between the lambda safe and the lambda MPF. This is how we actually also define what is needed for this, this project. The lambda MPF is also called diagnostic coverage. Now, in this scenario, with the Ceva team, the requirement, since this is an ASIL-B, the requirement was actually to reach an SPFM of 90%. Since this IP actually includes also on hardware safety mechanisms, so when we do the combinations, the need for the STL is actually to reach to 80% coverage. Okay, so in this scenario, our focus will be to reach above 80% for the STL alone. So, what is the common process of developing an STL? First, you will have, it's actually, if we think about it, and I will explain it in a minute, it needs a lot of teams to work on this process. Okay. First, we'll need, of course, the RTL team, the designers, to give us the design. Second, we will need the software team to build a basic STL. And then later, with iterations, we want to modify it and improve it to actually be able to cover more and more faults. Then we'll need the verification team to take both these words, the RTL and the software, combine them, simulate in their environment, and give us what we call a golden workload. Then we'll need actually the functional safety team. The functional safety team will look at all this information and look at it from the fault perspective. So this is where we do the fault analysis step. We look at all the possible faults that can happen in the system. And then the tools should provide some reports, learn from these reports, give back to the design teams and the software teams, debug, understand what do we need to improve. Do we need to improve from the RTL design perspective, or do we need to improve from the software perspective and give a new release of the STL? And this goes in iteration. Now, each iteration can be very time consuming. We're talking about weeks, sometimes months. And there is also sometimes some of these problems are actually hard to debug also in order to know how we can improve. Okay, this is just a summary of what I said. So we need multidisciplinary teams, software team, verification team, functional safety team. All the teams need to work in parallel together, especially in the debug phase, because you'll need both worlds of the hardware and the software. If we reach to the safety metrics that was required, which in this scenario 80% of the STL, then we are okay, we're done, nothing to do more. We can go to the certificate company and continue with this project. Otherwise, we will need to debug. And this is where the software team will go and improve the STL and reiterate again. In this project, Optima actually contributed to the step 3 and step 4, which are the fault analysis and the reports, and of course in the debug process with Ceva teams. So we changed the common way of the fault analysis, and we introduced the Optima Safety Platform. Optima Safety Platform, in this scenario, we we based our analysis on 3 different tools. One of them is static analysis, the other is design and workload constant analysis, and the third one is actually the fault simulation, which is common in the industry. But this is something that Optima actually implemented and developed. The next contribution was in the reporting. So the reporting have a lot of parameters that can be taken to the FMEDA report, can be tracked on how we are progressing. And also these reports include an insights on what happened on all the 3 engines. So this information was very useful to the debug phase, the design team and the software team. So the static analysis actually provided, it's kind of a static semi-formal engine. It provides and identifies which faults in the design cannot contribute or cannot influence the safety goals. They have no impact, they have no physical path between them and the safety goal. So this is why we can consider them immediately as lambdas. The constant analysis, on the other hand, is it was proven to be very helpful also. It's a dedicated engine that can identify non-toggling signals in the waveform or constants in the design. And this is very important because in some scenarios you have some configuration registers or some configuration of the IP, since this is a shelf IP. So each customer will actually configure it in a different way, and it will activate different areas of this chip. So in this scenario, the constant analysis can actually know in advance, just by running it, you can know that these faults will not be activated in this configuration or in this mode of the chip. Other cases of the constant analysis, if you see some non-toggling signals, which should be toggling, this is also part of the reports, and this actually can allow more faults to be detected by your safety mechanism. And of course, the fault simulation, where we actually inject the fault and run the simulation and see if the safety mechanism, or the STL in this scenario, can actually detect these faults. So the reports, as I said, it includes insights also from the engines. Besides just the metrics that can be used to the FMEDA report, it also includes insights. Which signals are not connected to the safety mechanism, which signals cannot influence the safety goal. The constant analysis can give valuable information like how many faults are actually being blocked by these specific signals. So if a specific signal should not be constant and it should toggle, we know how many faults is actually preventing them from being detected by the safety mechanism. So this way, the design team with the STL team, with the software team, can actually change the software in a way to toggle these signals and allow these faults to be detected. One of the smart ways that the Ceva team suggested is they know that they have 6 modules that are in the core of almost all the traffic in this CPU. So they say, instead of now focusing on the 14 and improving these 6 modules at the beginning, and since we know that a lot of modules are connected to them, we can assume that once we improve these and we toggle enough cases in the STL, much of the other faults will also be detected. And this is actually how we started the work. We started the iterations on focusing on these 6 modules. So instead of focusing on 14 or 15 million, we are focusing on 2 million faults. This is just an example of the reports that were provided, and we can see in this scenario how we improved SPFM, and each step we did that we improved these 6 models, we also saw a significant improvement in the overall SPFM. This is a graph of how we saw the improvement across time. The number of iterations we need in this scenario was about 10 iterations, where we started from almost 41, 44 SPFM, and we were able to reach 81% coverage on the STL after 10 iterations, which took approximately 8 weeks, all the 10 iterations. So approximately 1 iteration per week. The fault analysis time was about 3.5 days with the Optima Safety Platform. The design team and the software team were putting a lot of efforts in order to get these results and quickly come up with a new and updated software within 3 or 4 days from getting these results. This is a very quick response time, and this is actually what allowed us and allowed Ceva to finish this project and advance quickly with very few iterations. So it needed a collaboration between 4 different teams. It needed an ultra-fast analysis engine. It needed debug and recommendations that were actually given by the tools. Needed fast turnaround time by the hardware and verification teams. And of course the software team. The verification team will give requirements to the software team, and the software team will give a new updated software. We saw the importance of concept analysis in this scenario. And thank you very much for
maybe I can add
yes, be my guest.
a couple of words. I'm the safety project manager from Ceva side, who's working on this project. And before that, I worked for Intel and Mobile and a couple of other companies. Just to say one small correction, STL is not considered as the main safety mechanism
For the project.
Yes,
Yes,
it's actually considered as something that everybody is trying to avoid, because people are trying always to implement safety with hardware mechanisms, and whenever there is no other way, and actually we tried everything else, then we go to STL. And why STL is so difficult and so unique? Because there are very few companies in the world that can do STL. Maybe up to 10 companies in the world. There are many companies that are doing STL, but they are coming to those 10 companies for them to do the STL. And I'm not familiar with any other company in Israel that is capable of doing this kind of project. So I think this is a unique example of all Israeli project where the customer and the consultant are Israelis that are doing STL inside Israel without going to Germany or to United States or to Italy or Japan or to other places. So I think this is quite unique. It requires a lot of expertise, both in the hardware and in the tools. And this is the kind of cooperation that we need together with all.
Very nice.
Thank you very much.